Morning, everyone. Today's lecture is an introduction to nuclear processes, and I'm going to specifically talk about radioisotopes today, but this is an introduction to other nuclear processes. So, in an atom, most of the volume of the atom, as I've talked about, is occupied by the electrons, right? So, the electrons are much larger in physical size than the protons and neutrons, but they have almost none of the mass. Protons and neutrons are 1,800 times heavier than electrons, but they're much, much smaller in size. So in this depiction of an atom, the nucleus is about 100,000 times smaller in diameter than the entire atom, the part occupied by the electrons. So I've actually drawn this dot about 1,000 times too big in diameter to accurately represent the relative size of the nucleus. So the nucleus is extremely tiny in an atom, but most of the weight is there. And the fact that it's so much smaller than the whole atom tells you some things about how different nuclear processes are from chemical processes. So a chemical process is one where, like a chemical reaction, like the combustion of methane, the atoms in the molecules rearrange themselves into other molecules and energy can be released, either absorbed or released. In a nuclear process, the actual nuclei of atoms change. And that can involve far more energy because since these particles are so much closer together, they're bound together with much stronger forces than the molecules are bound together into atoms. And so the energies involved in a nuclear process are way greater. That is why a nuclear weapon is so powerful, and why nuclear power, in a nuclear power plant, the fuel stays in there for years before it's depleted, before it runs out of energy, because nuclear processes contain or release far more energy than chemical processes. So here's an example of a chemical process. This is a methane molecule and two oxygen molecules. Methane is a combustible gas, and when these react, the atoms rearrange themselves into different molecules, and energy is released in this case. So it's an exothermic process. So why is it exothermic? Because these particles, these molecules, are more tightly bound than the ones that go into it. So some of that extra binding energy comes out as exothermic energy. So when this occurs, when combustion of methane occurs, it seems violent to us. There's flame and a lot of heat released, but the nuclei don't change at all. The nuclei of these atoms don't change at all. They probably don't even notice that anything occurred in the outer atom because these nuclei are bound together with way more energy than are the atoms in molecules. And when a nuclear change occurs, a far more energy is involved. Now, in our environment, nuclear processes mostly don't occur. There's some radioactive material in our environment, but mostly what occurs in our bodies are chemical processes. There's no nuclear processes that are a natural part of how your body works. And there's very little nuclear processes going on around us. There are important nuclear processes in nature, like, for example, the process that generates energy in the sun is a nuclear process. And that's what makes the sun shine so brightly and has been able to shine so brightly for billions of years without running out of energy because nuclear processes are so energetic. So here is that process that occurs inside the sun. Now, these are not atoms. These balls are not atoms. They're supposed to represent protons and neutrons. So red ones are protons, gray ones are neutrons. And the process that occurs in the core of the sun is called thermonuclear fusion. Fusion, what is fusion? It means two things sticking together. You know that the strong nuclear force is attractive between protons. The protons repel each other by the EM force, but if they can get close enough together, they'll feel that attraction of the strong nuclear force and bond together. And that's what happens in thermonuclear fusion inside the sun. The reason it happens there and nowhere else is because the high temperature of the sun is causing these particles to move around at super high speeds, and so they can actually approach close enough to undergo fusion. So protons are fused together and they make what's called an alpha particle, which is the same as a helium-4 nucleus. Helium is element number 2, right? Two protons and two neutrons together is called helium-4. So what's happening in the core of the sun is protons are going away and helium-4 nuclei are being produced, and that's very exothermic. When a pound of protons turns into a pound of helium, the amount of energy that's released is about 45 million times greater than when a pound of gasoline and oxygen burns in the engine of your car. So it's a much more energetic process. So that's typical of nuclear processes. They release way more energy than chemical processes. This is another nuclear process that occurs in older stars. 3 of these helium nuclei come together to form a carbon-12 nucleus, and this is why carbon-12 exists. This is where the carbon-12 in your body came from. There are other nuclear processes that produce other elements. I'll talk more about this when I talk about thermonuclear fusion. This is where most of the elements that make us up are produced inside stars. And so it's a very important nuclear process for the existence of the elements. Okay, now, today I want to talk mostly about radioactive elements. So first let me introduce the term isotope. So what is an isotope? Well, you know what an element is. Every square on the periodic table represents an element, and each element is distinguished by its atomic number, the number of protons in the nucleus of each atom of that element. So hydrogen is element number 1, helium is 2, lithium 3, and so forth. So they're all different by their atomic number. Now, neutrons can also exist in atomic nuclei, and an atom can have 2 atoms of the same element, but different numbers of neutrons, same number of protons, but different number of neutrons. Those are called isotopes of elements. So there's another kind of chart called the Segre chart, or the chart of the nuclides, where every square is not an element, but an isotope of an element. And the way they have it arranged, the vertical position is the number of protons in the nucleus, and the horizontal position is the number of neutrons. So for example, oxygen-16 has 8 protons and 8 neutrons. All oxygen atoms have 8 protons, but oxygen-16 atoms have 8 neutrons. They call it oxygen-16, is because 8 protons plus 8 neutrons is 16 particles in the nucleus. So the bulk of your mass is oxygen, because there's so much water in our bodies, and most of that is oxygen-16. It's that isotope of oxygen, but a small fraction are oxygen-17, 8 protons and 9 neutrons, and a small fraction are oxygen-18, 8 protons and 10 neutrons. Those are both isotopes of oxygen that exist in our world. All these black squares represent what are called stable isotopes. So they're stable as far as anyone knows, which means they will remain what they are forever without switching into another isotope. And you can see several of the elements that are important in our physiology have multiple isotopes, like nitrogen and carbon. Carbon-12 is the most abundant isotope of carbon, but some of it is like 1% or so is carbon-13. So part of your mass that's carbon is carbon-13. Now these different isotopes behave almost exactly the same in terms of the chemical processes that they are involved in your body. So it doesn't really matter if a water molecule has an oxygen-16 or an oxygen-17 or an oxygen-18 oxygen atom. It behaves like all other water molecules for all practical purposes. So these are the stable isotopes. There are also what are called radioisotopes, unstable isotopes, and you can see there's a lot of them here. So for instance, oxygen-23 has 8 protons and 15 neutrons. That is a radioisotope of oxygen, which means it doesn't hang around forever. It can exist for a while, but eventually undergoes what's called radioactive decay and switches into another isotope. In the case of oxygen-23, that decay process is called beta minus decay. What happens is a neutron switches into a proton. It's got 15 neutrons and only 8 protons. That is not very stable, and it's more stable for one of those neutrons to switch into a proton. So instead of 8 protons and 15 neutrons, now you'll have 9 protons and 14 neutrons, which is fluorine-23. So oxygen-23 decays into fluorine-23, which is also a radioisotope. It decays into neon-23 by the same process, which decays into sodium-23, which is stable. So these radioisotopes mostly don't exist on Earth because they're radioisotopes. They're quasi-stable and eventually switch into other isotopes. So if these isotopes existed when the Earth formed, they mostly don't exist now because they're radioisotopes. Here's the whole chart of the isotopes, and you can see there are thousands of squares on this. It's hard to see the squares on this image, but there are thousands of them. And the color, the black ones again are stable isotopes. The colored ones are radioisotopes, the color indicating the decay mode. So for instance, the blue ones are beta minus decayers, where a neutron switches into a proton. Not surprisingly, the ones on the neutron-rich side of the stable isotopes tend to lose a neutron switches into a proton to make it more stable. So again, most of these radioisotopes don't exist on Earth because they're radioisotopes. They've gone away if they were here to begin with, but some of them do. Now, one of the most interesting things about radioisotopes is that the rate at which a given radioisotope decays away has a very predictable form. And to discuss why this is, I want to first talk about dice. You know how these things work. When you roll one of these, if it's a fair die, it has a 1 in 6 chance of rolling each of the numbers, right? 1 in 6 chance of rolling a 1, 1 in 6 chance of rolling a 2, 3, 4, 6. So if you roll a bunch of them, this is about 1,100 dice. About a sixth of these are going to show 1. Now, I've never counted the ones in this picture, but probably about a sixth of them are showing 1, because each one of these dice had a 1 in 6 chance of rolling 1. So you could do an experiment where you roll this many dice, remove the ones, and if you count what's left, that should be about 5/6 of what you started out with, right? Because 1/6 has been removed, 5/6 are left. If you then roll that number again and remove the ones, it'll reduce its number again by a factor of 5/6. And this is the result of a computer simulated experiment of this, where I programmed an Excel file to simulate the rolling of 1,000,000 dice. That would be a tedious experiment to do in reality, but Excel can do it in a couple of seconds by simulating it. So what it did was it chose a 1,000,000 random integers 1 through 6, 1 or 2 or 3 or 4 or 5 or 6, with an equal chance of choosing each one. And after choosing 1,000,000 numbers, it wound up with about a sixth of them were ones. And it removed those from the 1,000,000. What it had left was 833,299 that didn't roll 1, right? In other words, that's the number of choices of 2 through 6 that it chose. That's very close to 5/6 of 1,000,000. It's not exactly 5/6, but it's very close to 5/6 of 1,000,000. So what the program did then was to take that number, 833,299, and choose that many random integers 1 through 6 and remove the ones. And it had 694,552, which is very close to 5/6 of 833,299. And it did this 15 times. So it rolled the dice 15 times, and every time removed the ones. And after 15 rolls, wound up with 64,844. So now you can see how well behaved this is, because if you take 1,000,000 and multiply it by 5/6 exactly, instead of doing this computer simulation, and then multiply that by 5/6 and multiply that by 5/6 15 times, the number you wind up with is 64,905. That's very close to 64,844 that this simulation produced after 15 rolls. The point being, even though these are random events, like the rolling of dice, because there's large numbers of them, it still behaves in a pretty non-random way. It's a very predictable reduction in the numbers. And this kind of reduction is called an exponential reduction, this kind of a curve. And you can talk about the time scale of this with what they call a half-life. The half-life of this experiment is about 3.8 rolls. Now you can't have 0.8 rolls of a dice, but you understand, you roll it 3.8 times, and you reduce the number of dice by a factor of 2. So after 3.8 rolls, it reduces to 500,000 dice. After another 3.8 rolls, it reduces to 250,000 dice. After another 3.8 rolls, it reduces by 125,000 dice. So things that happen at random that reduce by exponential reduction like this they usually talk about the half-life. You could just as well talk about the 3/4 life, the amount of time it takes to reduce by 3/4. That would work, but it's traditional to talk about the half-life. And there's phenomena that behave this way in nature. For example, the density or the concentration of a medicine in your bloodstream. So what's shown here is the concentration of some sort of medicine like aspirin or something in your blood plasma over time. Time is on a horizontal axis, concentration on the vertical axis. So when you take a medicine like aspirin, it goes into your bloodstream pretty quickly, reaches its peak because it's going into the bloodstream through the digestive system, but then it starts being removed from the bloodstream because your body doesn't know you want the aspirin there, and it's got systems that remove things like the kidneys and the liver, remove stuff from the bloodstream which are not supposed to be there. And there's a certain randomness to the way that happens. So for example, an aspirin molecule, when it goes through your heart, it has a certain probability of heading toward your kidneys. So that random chance of heading toward your kidney gives the removal of aspirin from your bloodstream certain probabilities. Now there's evidently numerous ways that the body removes stuff from your bloodstream, but they all have kind of probabilities involved with them. And so you get this exponential reduction of the concentration of a medicine in your bloodstream. And medical people have to know this. Different medicines have different half-lives in the bloodstream. So if you're taking a painkiller like aspirin, it reduces by a factor of 2 every couple of hours. That's why you got to take more, because it's being actively removed. So here's an example of exponential reduction of something that occurs in our bodies. And of course, another example is radioactive decay. So polonium-210, for example, is a radioisotope of polonium, the element polonium. It decays into lead-206 by what's called alpha decay. It spits out what's called an alpha particle, 2 protons, 2 neutrons. And it does so with a half-life of 138.376 days. So if you had 100 grams of polonium-210, put it in a safe, after 138.376 days you come back, there'd be 50 grams left, right? It would have reduced by a factor of 2 over that many days. After another 138.376 days, it would reduce to 25 grams, and then to 12.5 grams, and so forth. So that's the half-life of polonium-210. So, and every radioisotope has its own half-life, and there's a wide range of half-lives. So hydrogen-7, for example, is a very unstable isotope of hydrogen. The nucleus is a single proton and 6 neutrons. That's way too many neutrons. It's very unstable, has this extremely short half-life. You can see this is a tiny, tiny fraction of a second. Beryllium-13 also has a really short half-life, 1/2,000,000th of a second. Carbon-22, 1/161st of a second, much longer than these other two, but still pretty short. Carbon-14, 6 protons, 8 neutrons, that has a half-life 5,730 years. So that's significantly longer. This is an important radioisotope, as we'll see next time with radiometric dating. We have this radioisotope in our physiology because it's in the air, and we get our carbon from the air. So something like 1 out of every 100 trillion atoms in your blood, in your body, is carbon-14. So there's this carbon-14, or this radioactive isotope that naturally exists in our bodies, and it's not man-made or anything. This has always existed in the Earth's atmosphere. So we actually have some of this radioisotope in our bodies. Rubidium-87 has a half-life of 49 billion years, so that's much longer than carbon-14. And we'll see that's also an important isotope in radiometric dating, but of rocks. Tellurium-128 is the longest half-life I could find. So this is much, much longer than the present age of the universe. So for all practical purposes, this stuff is stable. And it could be that some isotopes that we consider stable are all actually radioisotopes, but nobody's ever seen one go away because the half-lives are so long. But I just wanted to show you that each radioisotope has its own half-life, and there's a huge range of half-lives. Some are way less stable than others. Okay, this is a list of some radioisotopes that exist on Earth simply because their half-lives are so long that they've hung around since the formation of the Earth. Even though the Earth is like 4.5 billion years old, it's really old. But some of these radioisotopes have a sufficiently long half-life that they still exist, even though the Earth has been around for so long. And you can see they have very long half-lives. These are multiples of the age of the universe. So cadmium-116, its half-life is 2 billion times the present age of the universe. So it's, you know, it's any cadmium-116 that was originally here is still here, or almost all of it. And it goes, you go down half-life. The shortest half-life, uranium-235, it's about 704 million years. That's only about 5% the age of the universe, or about 15% the age of the Earth. So its half-life is shorter than the age of the Earth, but it's still long enough for some of it to have persisted since the formation of the Earth. So there are thousands of radioisotopes with shorter half-lives than this. They don't exist on the Earth because the Earth has been around for a sufficiently long time that they've gone away. And uranium-235 is about the shortest lived primordial radioisotope that we have here. And that's fortunate for us because that's the isotope that's used in nuclear power. Okay, so these radioisotopes do exist on Earth even though they're radioisotopes because they have a long half-life. There are other radioisotopes that also exist on Earth, not because they've persisted since the formation of the Earth, but since they're actively formed. And I mentioned carbon-14 is formed in the atmosphere of the Earth by what happens is these high-speed particles come out of deep space and slam into nitrogen-14 nuclei and turn them into carbon-14. So these are called cosmogenic radioisotopes that do exist on Earth. So you can see there's some of these as well. And here's the process that produces carbon-14. These very high-speed particles called cosmic rays are coming out of deep space. We don't know where they're coming from exactly, but they slam into the atmosphere and can cause some nuclear changes, like the formation of carbon-14. What happens is there's a shower of particles, and some of those are neutrons. Those neutrons can be absorbed by a nitrogen-14, turning it into a carbon-14. So these are all processes that produce carbon-14. Carbon-14 is also a radioisotope, so it's constantly decaying away in the Earth's atmosphere. So here's the process that makes it go away. So it's being formed in the atmosphere and it's also decaying away. And so the level of it over time stays about the same because both are occurring. It's being formed and it's also going away. About 1 out of every 100 trillion atoms, 1 trillion carbon atoms in the atmosphere is carbon-14. And because of that, about 1 out of every 1 trillion atoms in our body is carbon-14. We'll see the significance of that to radiocarbon dating next time when I talk about radiometric dating. Let me just mention one more thing. Uranium, the heaviest element that we have naturally occurring on Earth, has 2 isotopes that exist here. They're both radioisotopes. Uranium-235, which we use in nuclear power, and uranium-238. And these have these long half-lives, 704 million years in the case of 235, 4.5 billion years in the case of 238. Now these decay into isotopes that are also radioisotopes. You see uranium-235 switches into thorium-231, which has a 25-hour half-life, so that decays almost immediately afterward. But this decays into another radioisotope. They keep decaying into radioisotopes until you get lead. Uranium-235 winds up as lead-207. Uranium-238 winds up as lead-206. So there can be many decays before the isotope winds up as stable. All right, and I'll talk about these decay chains of uranium next time when we talk about radiometric dating. Okay, that should get you started on the exercise.